Well, let's see if we can prove this theorem, which says this in this isosceles trapezoid, where we've got the bases up here and we've got the legs over here, the congruent legs that is, we can prove that these angles at A and D are congruent, as well as the angles B and C. Let's get to it. Let me draw this auxiliary line. I know that for any line and any point not on the line, there's exactly one line, CH, that I can draw through C parallel to AB. How's that? That's what we call the parallel postulate. Now, that's going to make an interesting figure for us. That's going to make, jumping ahead there, that's going to make a parallelogram. And because it is a parallelogram, we can say this is a property of a parallelogram. Opposite sides are congruent, as well as opposite angles and other things, but we're just going to use that. And now I see something interesting. I've got a pair of parallel lines here. I made them parallel. So postulate 15 tells me that this angle and this angle are congruent because they're corresponding angles. Nice. So now I suppose what I could do up here, transitive property tells me since these two are congruent, then these two are congruent. You could say the I word, you could say it's isosceles, or you could just say, pull out this theorem. Oh yes, remember that, theorem without words. So I've got these two congruent sides from chapter 4, then the opposite angles are congruent. And again, that's going to tell me, let me clean this up a little bit, using the transitive property again, if angle 4 is congruent to angle D, and angle 4 is congruent to angle A, then angle A is congruent to angle D. Wow, pretty neat. So let's clean up the drawing a little bit. Now that we've got this, we've got these two angles congruent to each other. I'll call them the blue angles. Now, I'm going to make a statement that the angles B and A are supplementary because they're consecutive interior angles. And when I have parallel lines, the consecutive interior angles must be supplementary. Now that's also going to be true of angles D and C. One red, one blue have to add up to 180. So if I combine these two statements, one red, one blue is 180, and the two blues are congruent, then I can conclude so are the red ones. You'd think I would have colored that red. Like I said, the two red ones are congruent as well. And I think that does it. So you've got, clean this up a little bit, you're given a trapezoid, isosceles trapezoid, and you have just proven that the base angles, the two blue ones are congruent, as are the two red ones. Well, let's prove the converse of the last theorem. We're only going to need one pair of congruent base angles here. We'll take the blue ones, A and D. Same thing, we're going to construct a parallel right there. We cut it the other way this time. And again, we have a parallelogram. Why? Because we made it so. And now we can say the properties of the parallelogram, congruent opposite sides, and this time, well, supplementary consecutive angles. Then I see that, wow, whoa, this is a lot going on here. 1 and 2 are supplementary. 1 and D are supplementary. So 2 is congruent to D, and since D is congruent to A, then 2 is congruent to A. Whew, I got dizzy in that. So angle 2 and A are congruent, and that does it for us. Because right now I can say this, ta-da! Converse of the base angles theorem, right there. These two are congruent by the transitive property, so are these two. Pretty slick. Well, here's an isosceles trapezoid for you, and we've been talking about these for a couple theorems. Now we'll introduce their diagonals, and we'll say the magenta and the green diagonal are congruent. And let's have just a quick demonstration why. Let's take this triangle, call that ABD, and let's reflect it. You see, this triangle is actually congruent to its overlapping partner here. That would be DCA. And they're congruent, as you can see, by side, angle, side. Side, blue angle, side. Over here, side, angle A, and side. So then corresponding parts of congruent triangles tells us that the diagonals are congruent. And there you have it. Pretty slick. And the converse is true as well, but, well, I'll let you prove that. We're going to take an arbitrary trapezoid here, and we'll take the midpoints of the two legs and connect them right there. And that gives us something called the midsegment. So MN is the midsegment. And this theorem says, well, it's the average of the bases and it's parallel. Let me give you a way. We're not going to prove it. Instead, I want to share an illustration with you. Let's shade it all in. And I want to chop it like this. I'm going to cut pieces this way. This is my own theorem. And if we were to move these pieces around like this, and like that, what have we got? Well, we've converted it into a rectangle. And you see, this segment, the rectangle is the same as the height of the trapezoid, but the width of the rectangle is the width of the midline. Sorry, midsegment. That's why it's the average of the bases. You'll see more of this in the section on area, chapter 11. Well, this theorem tells us that a kite, like the one we have here, has diagonals, like our red and blue ones here, that are perpendicular. Well, that's pretty convenient. Looks like a kite, like Charlie Brown flying that. But let's see if we can prove it really quick. I think we can. All right, let's just start over. I'm going to use this theorem, the converse of the perpendicular bisector theorem. Dang, that's a lot of words. Let's just go right to a picture here. Let me illustrate it this way. Perpendicular bisector theorem says that if I've got a figure like this, I've got a point y that's equidistant from the endpoints of a segment. Looks like an isosceles triangle. So if I moved it like this, all those points are equidistant from the endpoints of the segment, W and X, and therefore they are on the perpendicular bisector. Got it? Okay, that's from back in chapter 5. So let's move over to our other figure. I'm going to say that this point B, well, it's right there. It's the same distance from C as it is from A. And that means B is on the perpendicular bisector of AC. So that's pretty neat. Well, D is also the same distance from A as it is from C. And therefore, D is on the perpendicular bisector of AC. And we know that 2 points determine a unique line, ray, or segment. Therefore, I can conclude that BD, that is the red line, is the perpendicular bisector of AC. So not only do you get the right angle, but you get this too. These two pieces are congruent. And remember, the red is the perpendicular bisector of the blue. The blue is perpendicular to, but does not bisect the red. Well, here we have a kite. And you see it's a kite because we have exactly 2 pairs of congruent sides here that are adjacent, and these 2 pairs are also adjacent. And this theorem tells us that, well, we have exactly 1 pair of opposite angles congruent. The other angles at B and D are not. How about a proof? You up for it? Okay, here we go. Let's draw this. Any 2 points determine a unique line, ray, or segment. Then reflexive property, and you can see those 2 triangles, they jump out at you right away. we've got a pair of congruent triangles, of course, by side, side, side. And once I've got that, by the corresponding parts of congruent triangles, there's the acronym spelled out for those of you unfamiliar with the old textbook. And that's it. So now angles A and C are congruent.